Okay, I see that it's the top of the hour. So welcome back, everybody, to the whole Heliosphere and Planetary Interactions meeting. I'm Sarah Gibson. I'm happy to welcome you to our third day after our data and modeling gathering first day. Today, we are going to have sessions on specific events during WHPI and impacts of both CMEs and high-speed streams to various planetary systems. We'll be doing that this morning with some speakers and some focused discussion. Then we're going to have posters after a short break. Catherine, could you go ahead and put the poster link in the chat again? You're able to view the posters at any time. However, during our designated poster time, we'll first have in plenary presentations from the poster presenters, very short, just telling you what their poster is about. And then we'll be able to drop into the posters through Zoom breakout rooms. So you'll be able to jump around and see many different posters. And then we'll come back and have a plenary discussion where hopefully we can start to see some of the connections between the work that's been done and get some ideas for collaborations moving forward. I want to remind you all this morning that as in the other days, we are doing our questions using Slido. So if you have a logistical question, you can put it in the Zoom chat. But if you have a question, a science question, please use the Slido. And somebody, Catherine, you want to go ahead and put up the Slido link again for people. That link will keep popping up from time to time because we realize people drop in and out and they lose the Zoom chat, so they may not have it. So you're able to get into the Slido to ask questions. You can identify yourself by assigning your name. And we use those questions to coordinate the discussion, both after the focus talk sessions this morning, and then also during our larger plenary discussion later today. Please be aware that you can answer Slido questions that get asked. So if somebody has asked a question, you have a reply to it, feel free to go in and make a reply. Speakers can also do that at any time so that the Slido then becomes an avenue for a written discussion in addition to the verbal discussions we're going to be having during the plenary and on the Zoom. Okay, did I forget anything in terms of logistics? Catherine, did you have anything you wanted to add?
No, I think you covered it. It looks like the link might have not quite worked for the poster gallery, so I'm just reposting that, and this one you should just be able to click on.
Yeah, so the two things you're seeing in your chat, excuse me, are a link to the posters, which allows you to preview them before we have our Zoom breakouts, when you get to go to the individual posters and meet with the poster presenter and chat with them. And then the second thing is our usual Slido link, so you can ask questions during the talks that are about to occur now, and they'll be addressed after the talks. So without further ado, I will go ahead and hand off to the chairs of the next session, who are Gina DeBraccio and Rachel Philwitt. So take it away.
Yeah, thanks so much, Sarah. So welcome back, everyone. Good morning, good afternoon, in whatever time zone you happen to be located in. So this is the second Working Group 4 session. So Working Group 4 is the impacts of solar activity throughout the heliosphere. So we're looking particularly at CMEs and how they're affecting various systems, comets, planets, the great old Earth system, a variety of different things. Today, our working group topic is focused on specific events to WHPI, and WHPI has a number of campaign periods, which you have heard about already during this meeting. And what I want to turn your attention to is from April 28 to May 7 of 2021. And so you can actually go on the WHPI page and pull up that campaign period if you're interested. And there was some CME eruptions during that time period. And so this is something that our working group is really interested in hopefully gathering all of our relevant expertise and working on in the future. Let's see, so we're going to have two speakers today. Amelia, who is joining us from the University of Helsinki, and then Erica Palmerio. And as Sarah just said, we are going to be holding the questions that you submit in the Slido to the discussion after both of them are finished. All right, I think that's all I have. So Amelia, if you're ready to go, I'm excited to hear what you have to share with us.
Yeah, sorry, now I'm unmuted. So thanks, Rachel, for presenting me and asking me to talk about here. So I hope you can see my slides now. I'll put them on the presentation mode just in a sec. Yeah, you can now see them.
Perfect. Yeah.
Okay, great. So I'm talking about two events here that occurred during the white solar minimum condition that were both observed at Parker Solar Probe. And in particular, I'm focusing here the interaction of them with the preceding solar wind structures. So these were occurring both when the Parker Solar Probe was relatively close to the sun, so 0.5 astronomical unit. And here are two of these papers. So the other one is led by postdoctoral student at the University of Helsinki, Sanchita Pal, and she will be submitting this very soon to the Geophysical Research Letter. And this other one is the March event from 2019 that we just submitted the paper to the Astronomy and Astrophysics. And this paper that Sanchita is leading from June 2020, this is the focusing on this flux rope part, while in this March 2019 event, we are focusing on the sheath region. And here are some similarities between the CMEs. The both were associated with relatively slow streamer blowout CMEs. They were both related to the relatively slow interplanetary CMEs. In this paper studied by or led by Sanchita, there was no shock, but in this March 2009 event, there was the shock and sheath. And also similar to both was that the interaction between this heliospheric current sheet was very important for these events. And this shows this nice three-part CME in this June paper that I'm discussing the first. There was not much seen in the inner coronagraph of the stereo A, only the prior swelling of the streamer and some depletion. And the Solar Dynamics Observatory did see hardly nothing on the disk, so this could be then associated with or classified as a stealth CME. And then there's a paper made by Erika Palmeri and Christina Keiver. They showed that this CME was actually deflecting towards the heliospheric current sheet. And what Sanchita found out that this was a multi-stage and sympathetic breakout eruption, so there were several flux systems associated with this event. I'm not going into the detail, just mentioning that they were nicely corresponding to also to the EUV observation, and there were actually 3 eruptions. So first a narrow jet-like CME, then cloud-like coronal mass ejection that didn't have a very clear structure, and then finally this more prominent stream blowout coronal mass ejection. And then she also looked at how different structures in the CME were propagating in this stream blowout CME. So here's the height velocity diagram. Red one is a cavity and blue is the core. She looked the J maps and then recorded how they were propagating, and finding out that in the beginning of the event, the core was actually initially faster than the cavity. And this has been observed in some previous studies also, and has been taken as the additional acceleration coming from the reconnection outflow below the CME. And then she went and looked the in situ observation. So here you can see Parker Solar Probe observation of the magnetic field components. This is the phi angle of the magnetic field, the longitude angle, velocity, density, temperature. Here are pitch angle distribution, and finally the plasma beta. And here's the close-up to the CME leading edge, the magnetic field magnitude and the components. And what PSP saw was the very clear flux rope event without a leading shock. It had a declining speed. And one thing she was focusing on was looking at the suprathermal electrons that showed the switch in the pitch angle direction, and what she was also then able to see or associate to this crossing of the heliospheric current sheet. And there was also signatures of the clear that there was likely reconnection had happening at some point at the leading edge of this coronal mass ejection. So this part is close up somewhere from here. And so this is the schematic she has made of this event. So this is red line is the heliospheric current sheet. You can see here the flux rope and then the magnetic field lines that are draping around this CME. And she also studied the flux that was, or the flux asymmetry, to see that how much of the initial flux of the CME was eroded. And she found that it was quite substantial part already at this 0.5 AU, so almost like 40% of the initial bolloidal flux had been eroded. And maybe one thing that was like favoring this one was this squeezing of this flux rope with this heliospheric current sheet. In the paper, she has much more detailed analysis also of the solar observation and the solar magnetic flux that is eroded in this eruption, but here like focusing here on this interplanetary interaction and making this case that this was highly eroded flux rope, and this interaction with the heliospheric current sheet was the key. And then I'm hopping into this other paper that March 2019 event. This is from the paper by Dario et al. That was detailed analysis of the CME and large-scale connection SCPs and the general structure of the flux rope. You can see here this nice coronal mass ejection, and this is the depiction of that the CME was a little bit propagating north from the ecliptic. And this is also a paper from this Dario et al. Paper. So you can have here velocity components. This is density, temperature, and magnetic field. So just featuring out that you can really in this like larger picture see the flux rope and then this compressed sheet region ahead of it one. So this event was sandwiched between slower and faster solar wind stream. And in this pitch angle panel also you can see here the change in the pitch angle distribution. So there was the crossing of the heliospheric current sheet. You can see here also the tiny flip occurring in the sheet of the CME. I'm getting back to this feature soon. And also Dario et al. They reported that the CME was generated or was led by the two relatively weak interplanetary shocks with Mach numbers just reaching 2 and velocity about 370 kilometers per second. And then what we did in our study, we were looking more these properties of the sheet and especially the fluctuation properties. And here you can see the magnetic field components by these colors. The black line is the magnitude, this longitude angle of the magnetic field, solar wind velocity, density, and pitch angle distribution. And what is the most striking here are these few sharp field directional changes in this sheet that when we zoomed into this one, they looked like the reconnecting current sheets. Unfortunately, plasma data had a gap, so we couldn't, it was not like conclusive, but it had this very nice step-like magnetic field change and the dip in the magnetic field. And likely these were heliospheric current sheets crossing. There was associated also with the flip of this direction of the on the direction of the heat flux. Another interesting feature is that this sheet has here also this two-step speed profile, so increasing quite substantially during within the sheet region. And then we studied this fluctuation. So you can see here our fluctuation, normalized fluctuation amplitude. So magnetic field at time t, and then minus at the little bit later time. T is the time scale, and this is the compressibility, and then the final panel is this partial variance of increment that tells you, yeah, thanks. That tells about these sharp structures like current sheets and things like that present. And you can see that this sheet is, firstly, it is clearly more fluctuating than the preceding, and then also that the end part of the sheet is more highly fluctuating. And I can just quickly mention this, that we also look these other fluctuation properties, residual inertia and cross helicity, to getting information that what direction these fluctuations are propagating in relation to the sun. And also we saw some differences between this front part and the leading part of the sheet. And in the middle of the sheet, there was this clear velocity shear region that was also associated with the heated solar wind, so increased temperature. And I will show here the schematic of this event. So here's the heliospheric current sheet draping through the ejecta. So this is nothing like into the scale this event, but it could be that the CME ejecta accelerated the wind that compressed into this lower solar wind ahead and then created this region that looked like the stream interface region. Okay, so this is basically short summary that there were two events that we studied, both interacted with the heliospheric current sheet for June 2020 that led to the significant erosion, probably due to this squeezing. And in this 2019, it was likely this warp heliospheric current sheet that was swept into the sheet and divided the sheet into the two different type of the flows based on the speed and fluctuation properties and this heated portion. And then in the future, hopefully the combined observation by Solar Orbiter, Parker Solar Probe, and the Colombo provide more chances to see these kind of the events, in particular close to the sun. But yeah, thanks. That was all I had.
Yeah, thank you very much, Amelia. So once again, if anyone has questions, please enter them into the Slido. And then after our speakers are all finished, we're going to go ahead and have our discussion time. So next we are going to have Erica Palmerio. She's joining us from UC Berkeley and UCAR, and she's going to talk to us about using planetary missions to identify and follow transient structures in the solar wind. Thanks very much, Erica, and take it away.
Thank you. I will start sharing. Can you see the slides?
Yep, looks great.
Okay, and also we'll have to make sure that it moves the page because there have been some problems. Okay. Thank you for the introduction. I will be giving a very quick overview on using planetary missions for heliophysics purposes and like for studying what's going on in the solar wind. Where the field of heliophysics is now is that it's becoming more and more a field about the entire heliosphere. So we're no longer focused uniquely on the Sun-Earth line, which is something something that is developing more and more in these more recent years. And we have had a bunch of heliophysics missions launched throughout the year, starting from Helios in the 70s. But what if these data are not enough? Well, data are never enough. We always want to have more and more data. We need to get as many data points as we can, and planetary missions are often extremely useful in providing extra observations and providing these extra data points throughout the heliosphere. And in this talk, I'm going to be focusing mostly on the inner heliosphere, but that's obviously not limited to the inner heliosphere. And here in the figure, there is an example of a period in May 2012 that we have studied recently, and the panel on the left is which data points we would have without planetary missions. So we would have Earth, stereo A and stereo B, and then instead this is what the situation was with actually including planetary missions and a bonus astrophysical mission, that is the Spitzer Space Telescope. But you can see how much the view of what the sampling point throughout the inner heliosphere have increased tremendously for this period. So in order to add these extra data points for the inner heliosphere, what can we learn from planetary missions? So there are either direct measurements. So some spacecraft are equipped with magnetometers, plasma, or particle instruments, and magnetic fields and plasmas and plasma instruments can sample directly the solar wind, well, of course, during cruise phase, but also often during an orbiting phase when a spacecraft is exiting the planetary magnetic environment and entering the solar wind close to the apoapsy apoapsis portion of the orbit. And particle data can be used at nearly all times. And here there are some examples. So for example, there is example from this study from Good et al. Where they looked at the magnetic structure of CME flux ropes at different heliocentric distances for radially aligned events. So between Mercury, Venus, and Earth. Here is a study of the solar wind and other measurements around Mars from Lee et al. About the September 17 CME and SEP event that also impacted Earth. But other sets of measurements that we can use to understand what's going on in the solar wind around a planet is more indirect measurements. So measurements that are a bit less usual for heliophysics. And in here for heliophysics, I mean the study of large scale solar wind transients. So CMEs, HSS, and SEPs. But still, these indirect measurements can still be extremely valuable. They can be used to infer the passage of a CME or a CIR. And some examples are, for example, here, this top line is the altitude at which Mars Express was crossing the magnetic pileup boundary of Mars. So when a CME passed, this boundary lowered tremendously. And from there, then we deduced that a solar transient was passing by Mars. Background counts at Venus here were used for comparison with modeling results by Luhmann et al. And here are neutron monitor data at Earth on the top compared with dose rate measurements by the Curiosity rover during cruise phase, which can be used to study SEP events and Ford-Bush decreases, even if the instrument itself is measuring dose rate, which is the amount of to quantify the amount of radiation, for example, to astronauts in the future. So now we can move to very quick bites of examples from what we can do with planetary missions to add this extra point during this recent solar minimum, so during the period of interest for WHPI. So we start by reviewing CME and HSS interaction event from August 2018. So the CME was a slow CME from a filament that is indicated here in mid-August 2020. And as the CME propagated, it was followed by fast solar wind from this coronal hole in the northern hemisphere. And we used WSA, Enlil, and the plus-cone model to model, to evaluate where this CME would be impacting. We also modeled a preceding smaller CME that you can see here in the simulation. And you can also see that Earth and Mars were very close to each other longitudinally. They were only separated by 8 degrees and then only 2 in latitude. So they were almost radially aligned. So that's actually a good event, a good example of a good occasion to study how the interaction between a CME and HSS happens. And here you can see this HSS that is not super fast. It's about 500 kilometers per second in the simulation, but it's following the CME. And then here are measurements, in situ measurements at Earth and Mars. The first preceding CME is clear at Earth, is the one in pink. Then this is in light gray is the main CME, and then in darker gray is the interaction region between the CME and the HSS. So at Earth we have this clear phases of what's going on. We have a very clear flux obstruction, and we have an HSS following it right after. But instead at Mars, okay, first of all, we don't have continuous solar wind measurements. So here are measurements from the periods in which Mars was in the solar wind, and in which MAVEN was in the solar wind for the magnetic field. And in lighter color, it's like lighter shade of the same in the same plot is the foreshock portion. And for the plasma data, we have Mars Express and MAVEN data of the solar wind. But the situation is much more complicated, and maybe not only because of how much of the data gaps that we have. So the first small CME is hard to distinguish, of course, because it was already very small at Earth. But then for the main one, it is actually like the nice flux structure from the first CME is completely missing in the second one. It is unclear whether there is a CME at all or what its extent is, but so this shading is a attempt at following the plasma profiles from Earth. So the situation at Mars is much more complicated. It suggests that, okay, of course, the CME encounter should have been much more flankish than at Earth, according to the simulation as well. But we are in the situation in which either we're seeing very, very little bits of a CME, or the following high-speed stream has basically engulfed and interacted strongly with this CME. Then another example is May 2019, which was a WHPI month of interest, the entire month. And that's because the star of the month was the couple of active regions, 12740 and 12741, which were two large and rather eruptive active regions that were placed in the middle of a very, very solar minimum sun. So here are a couple views of the two active regions from stereo A, and then when it rotated to Earth. This is the situation of the entire month of various planets and spacecraft. And the major eruptions from these two active regions, major here means that the ones that were detected in situ by something, are here, plus there was a CME more towards the end of the month that was not coming from these two active regions. But here is just a very, very quick overview of things that one can do. So here we have Mars, stereo A, and Earth. So we are covering a span of longitudes that are about 130, 40 degrees. And we can follow basically eruptions in longitude from a certain region as these regions rotate with the sun, obviously. So for example, at Mars, we have disturbed conditions seen in this region, which could be an HSS with the first CME, then the second, third, fourth, and fifth CMEs arrive between stereo A and Earth. We can follow, so stereo A and Mars were very close to being spiral aligned. So this this kind of period is also useful for studying. Okay, also useful for studying CIRs and HSSs that are supposed to be passing stereo A and Mars more or less simultaneously, but obviously we will be measuring something a bit different, and so on. This was just a very, very quick overview of how useful it is to be able to follow things, regions and active regions, eruptions and HSSs before having to wait for an entire rotation before these structures come back to Earth from our viewpoint, but as they rotate with the sun. And then very quickly, I will try. So this was another study of mostly focused on the CME-driven shocks and the spread of SEPs in the heliosphere. There were 5 eruptions followed at the end of 2020 between 26th of November and 7th of December, because there were 2 SEP-rich, SEP-rich CMEs on the 29th of November and 7th of December 2020. And we had 6, we modeled the CMEs and we created synthetic SEP profiles for these CMEs using WSA SETMOD. And we had 6 total observers, which are Earth, 3 heliophysics missions, stereo, Parker Solar Probe and Solar Orbiter, and 2 planetary observers, which were Mars-based spacecraft and BepiColombo. This was a very large study, but I will focus here on one small aspect that includes planetary missions, so spacecraft around Mars. So this is where the 2 eruptions went off. So with respect to Earth and Mars, this was the flare 1 and flare 2, and you can see them here in the plot. And here are 3 different energy levels of SEPs. In black, the measurements, and in the other colors, simulation data, simulation results. And Earth and Mars were basically along the same IMF line according to the ELIL modeling. So we would expect to see basically the same SEP profiles, which is from the two SEP-rich eruptions, which is true for flare 1. We see very similar profiles, but Mars instead is seeing only SEPs at lower energies from the second eruption. So that can help us also in validating models. So it means that probably Earth and Mars were not really on the same magnetic IMF line. Otherwise, we would have seen much more similar profiles and much more similar populations of energies in the SEPs. So very quickly, take home message, or I'll leave it like this. I don't know. Do I have time to go very quickly through this?
Yeah,
sure, go ahead. You can wrap it up.
Okay. So planetary missions have a lot to offer to heliophysics. They can complement all the more traditional data that we have from more classic heliophysics missions. And being able to follow different solar transients at so many, at as many locations as possible, it's useful not only from an intrinsically observational viewpoint, but also to validate models and theories. And coordinated efforts such as WHPI are excellent for this kind of studies because there are very many data sets. So these studies can involve lots of data, lots of people, and lots to work on. So thanks, everyone, and sorry for going maybe 1 or 2 minutes over time. Thank you.
No worries. Thank you so much, Erica. Okay, it's time for our discussion. So we have some questions in the Slido. Please keep entering them. We'll start the discussion, but it doesn't have to just go to our speakers as well. If anybody else has work that has been, from the observations of the WHPI campaigns, feel free to either write in the Slido or raise your hand and we can get you involved here too. But I'll jump in, Erica, since you're still unmuted. Let's start with a first question from you. I was wondering, it was great how you were showing the usefulness of the planetary missions for heliospheric purposes and different studies. Can you say a word or two whether there's useful information that we can get from these planetary missions when they're within the magnetosphere? For instance, I'm thinking of MAVEN measuring the SEP particles. So what information can we get about the heliophysics going on even when the spacecraft are inside?
Yes, yeah, definitely. There are things that can be very, very helpful even when a spacecraft is inside. excuse me one sec. For example, yes, SEPs, especially the most energetic ones, can be basically measured inside the magnetosphere at all times. So because these particles are so energetic that they don't really care about what they're passing through. Then obviously the more lower you go with energies, the more you have to be careful of what you are actually measuring. Are you measuring a solar wind population or a magnetospheric population? But there are also either other more indirect kind of measurements that can be used. So for example, for Mars, we showed the altitude of the crossing of the pilot boundary of the magnetosphere. Now what comes, for example, from the top of my head is something that has nothing to do with the inner heliosphere because it's about Saturn. But for example, there is a radiation that is emitted at Saturn from the poles, which called the Saturn kilometric radiation from the auroral oval. The Saturn kilometric radiation, which is basically, radio emission from the poles. And that emission is increased during solar wind, disturbed conditions. So it is a kind of measurement that is very, very, very like magnetospheric and very planetary, but is very useful for heliophysics as well.
Great, thank you. That is a perfect example. And I know we have Christina Lee online, who you're working with. Christina, is there anything else that you'd like to add with the MAVEN SEP observations that you've reported on? If, she raised her hand, if we can unmute Christina.
All right, thanks, Gina. Can you ask the question again? Sorry, guys.
Yep, no worries. I was just curious if you had any extra information that you'd like to give regarding some of the work that you've done with the MAVEN SEP observations and what they tell us about kind of the heliophysics going on there.
Okay, yeah, absolutely. I think Erica touched upon this, and I think Olivier talked about it yesterday in this presentation. I talked about it as well. You can use the SEP measurements, to look at timing, of course, of the CME structure when it impacts the observer or not. And, depending on the energies and if you see a velocity dispersion, that tells you how the observer is connected to the shock source for the SEP. So in this case, like the shock of the CME, and if you're well connected or not. So, there's been these very classical SEP profiles that many of you might have seen from Ian Richardson and Hilary Kane that shows you that depending on the shape of the SEP profile, that indicates how you may be connected to the CME shock source. So, we have this SEP data set from MAVEN. There's a SEP detector on the MAVEN spacecraft that's measuring SEPs at Mars, and I talked about this yesterday. It's been measuring SEPs since late 2014, and it's continuously making those measurements right now. So I think they're being used, just like Erica has shown in her presentation, they're being used as part of a heliospheric data set. It's another data set that's beyond 1 AU, that's not Earth or stereo. So I think it's adding a lot of value to our understanding of space weather events and how they're impacting different observers in the inner heliosphere.
Great, thank you so much, Christina.
Yeah.
Okay, I'm moving over to the Slido, and we'll give Erica a little break here. Sarah Gibson, I see you have a question for Amelia. Would you like to state your question out loud?
Sure, yeah. So thank you very much for your talk, Amelia. Really interesting events. And if I understood that correctly, they were both slow CMEs, and they both had these interactions with the current sheet. I was just wondering, in a more general sense, what your thoughts were about, how typical is this for solar minimum events? Is this only something you see during solar minimum? And what do you think is the benefit of doing studies during solar minimum for ICME studies?
I think actually this is quite typical because they were these stream blowout CMEs that I have understood they are quite dominating in the solar minimum, while at solar maximum we have this coronal mass ejection coming from these mainly from active region being much more fierce and interacting with each other. At solar minimum, although it's sometimes it's less ICMEs, but they are maybe a little bit more well behaved and do not have so complex interactions. So I think it's also very beneficial studying them at solar minimum. Although I think at some points at solar minimum, it can be actually quite pain to find the correct CME and ICME pair. But I think that's actually something I hope would be a little bit more easier now with these spacecraft that are going closer to the sun to make this connection. So that was actually one surprise that I have had over many years, that how difficult it is connect the correct events at the sun and in interplanetary space.
Yeah, we did some of this ourselves on the WHPI intervals, and you're right. You'd think it would be obvious, and it really isn't.
Yep. Yeah, that's actually that's always like amazes me that how complicated it is, and you always find something like extra on the sun, or you think it's like clear in the interplanetary space, and then you see that it's interacting with other events. But at least these seemed that they were interacting mainly with these heliospheric currency surroundings. So I think it's very, very nice feature that you can see a little bit like different type of the interaction than during the solar maximum.
Thank you.
All right, great. And then Rachel, I see that you have a question. Let's go with your question to Amelia, since she is unmuted as well.
Yeah, thanks. Yeah, so Amelia, I forget what specific date it was for, but in kind of the side information you had listed, one of the CMEs had some slow shocks that preceded it. And so I was wondering if there was like any clear interaction with those slow shocks in the data that you looked at.
Can I by the way detail that? Do you mean like slow mode shocks that you notice in the data, or do you mean in this March event that it was just preceded by these two slow speed shocks? Yeah, you mean the slow beat?
Yeah, the slow speed. Yeah. Yep.
Yeah, I think the CMEs were actually both somehow driven by this coronal mass ejection. They were very like, how do you say, very close to each other. It was only maybe a few minutes apart. They just studied in detail in this Dario et al. Paper, and I don't think they go any like too detailed like hypothesis that why there's two shocks instead of one, because there's clearly only one flux rope to be seen. So they just said, I think in the paper, that it's somehow connected to this CME interaction with this preceding solar wind and the like trailing fast stream. But relevant for this study that we made these slow shocks is interesting that how much do they process the solar wind fluctuation ahead? So are they like just like solar wind is more like nicely passing through the shocks, or is it like disturbing or destroying the turbulence ahead or generating the new ones? And based on this fluctuation that we looked, it seems that it did kind of very little in this case, because sometimes you can see a big change in the fluctuation if you have strong shocks. And for example, if you compare to the planetary magnetosheets, but here it was quite like minor effect. So more this processing seemed to be going on inside the sheet than at these relatively slow and weak shocks.
Very interesting. Thank you.
And Amelia, I was just curious if you know whether either of the events that you were showing, if they actually interacted with any planetary magnetospheres as they propagated away from the sun. Actually,
we didn't check that one. I think they didn't at least impact to the Earth, because otherwise we would have been certainly used this like multi-spacecraft opportunity. Sure. But I haven't been looking like at the later planets. Maybe Erika, you know about the, at least for the.
I was typing in the chat of Slido. Can you please
repeat the question? Yeah, yes. So I was just curious if either of the events that Amelia was reporting on, if we know whether they impacted any planetary magnetospheres. And so her answer was, at least in the inner heliosphere, that doesn't seem to be the case, but she wasn't sure past Earth if any of the other planets were impacted.
So I think that for the, I'm more familiar with the June 2020 event rather than the other one was March 2019. So for that one, I think that there was Mars close in longitude, but I haven't gone and looked at the data, but Mars should have been nearby longitude with PSP. Now, did it impact Mars? Not, I don't know, because the CME was very narrow, being a very stealthy, slow, not not spectacular event for the eyes, but there is a possibility, yes.
And I was quite like positively surprised at how much data you actually got from the close to the Mars. So you even had some magnetic field and plasma data there, and you could really see the CME.
Mm-hmm.
So that's great.
Yeah, we're really lucky with MAVEN observations, as Erica was showing, for the fact that we do observe the solar wind quite often. And for that reason, if we're lucky enough, when a CME or any other solar activity is passing by, we can have direct observations from it, which is great. Mary, I see you have your hand up if you'd like to unmute.
Yeah, so this was the question or comment I put in Slido. There's very nice GOES data with the new GOES energetic particle instrument for the November-September 2020 SEP events. And Erica, I'll send you a PDF that Brian Kress, who is the NOAA PI on that instrument, put together. It has 10 energy channels between 1 and 500 MeV, and so it shows the event over that whole time period really nicely. And so I just want to put in an advertisement that there's some very nice data at Earth as well for these events, and for this one in particular that people may not be aware of.
That's great. Okay.
Thanks.
And that is in Slido if you want to revisit the dates Mary was just saying. But Mary, while we have you, I believe that you were looking at radiation belt impacts from the May 2019 event. Is that correct? Would you be able to say a few words?
Yeah, and I'm going to be talking about those on the hour. So the only thing I'll add to what I'll say at 9:05 is that there were 5 CME events, as I think Erica pointed out, yes, for that time period. And the middle one was the most geo-effective. And it looks to me like also the strongest indicators in the solar wind for why it was most geo-effective. And so that's the one that we studied, we modeled with an MHD test particle simulation to reproduce the radiation belt response. And then we compared it with the CIR event at the end of August, beginning of September 2020, 2019, just to get a contrast between those two types of events and their effects on the radiation belt. So I'll talk about that at 9.
Great. Okay, perfect as advertisement for you then.
Yeah, and super cool that you're talking about the May 2019, like in 1 hour. So because I only had time to give a very, very short, like speed overview of the event, but super nice that you're going to go more in detail.
Yes, perfect. Just a reminder for everybody, you can keep inputting questions in Slido. You can raise your hand if you want to add to the conversation. And I see that Sarah Gibson, you have your hand raised.
Yeah, it seems like this might be a good time, and we can maybe even let Erica get a little more into the May 2019. It was a really interesting time period. Would it be okay if I showed my screen, Gina?
Sure, absolutely.
Okay. Let me see if I can do it. Kelvin, I think I can. So this time period, the May 2019, was a subject of our WHPI sprint activity. Can you guys see the Google page I have up?
Yes, we can see it.
And we had various people.
Sarah, actually, I have a very quick, because in my slide I called it WHPI month of interest because it was not a campaign month. So it's a different. What's the difference?
It was, campaigns are the ones you plan for in advance because the orbit of Parker Solar Probe.
Oh, yeah.
The months of interest are the ones that happen. The sun decides to do something interesting.
So
let me show you what the sun did interesting. So this is, let me make this big. And it's not awesome resolution, apologies for that, but you'll get the idea. Watch the active region that comes off and it goes pop, pop. And there's actually a chain of them, pop. This one's going to go off, pop. So during the month of May, and I think the one that Mary was talking about that was particularly geo-effective was probably right when it was right in the middle of the disk center. But I believe, and Erica, you can correct me if I'm wrong, but I believe Mars is off to this side.
Yes, it's 30, 40. So the stereo A was like almost quadrature, perfect quadrature. And then Mars was like 30, 40 degrees to the east of stereo A.
Okay, perfect. And so that gives us some interesting things to work with. And of course, and maybe you can show again what you put together, because you've got a lovely gathering it all. But we looked at, there are white light CMEs that are happening, for example. Federico Gasparini maybe can make some comments, because he looked at some MAVEN data of the atmosphere and also some Earth thermospheric responses. We had, of course, we've got you on here, Erica, and several other people, and Mary as well. So it's a really interesting month of interest for trying to tie together what's happening, because we're seeing a sequence of CMEs, which may complicate understanding which one is the one that's hitting which spacecraft. But it is an interesting month of interest. I'm going to stop sharing.
Great. And it seems like we got Ian's attention. So Ian, would you like to unmute?
Yeah, I was just wondering, Sarah, was that the time when Barbara showed those two coronal holes that dislodged and sort of reset at about 290? Was that the same time?
That's right. That is the time when the elephant's trunk got burned or something. So there was a low latitude coronal hole driving high-speed streams in that area. And then it basically was disrupted by this month and then reformed.
Yeah, not surprising with all those things blowing off. That's pretty cool. Making connections.
Awesome. Okay.
I was going to see, is Federico on? Because I would love to have him comment, because he's done some great work on this.
He just raised his hand.
Hi, Sarah. Yes, I did look into the May 2019 period, and specifically looking at the response at Earth in the Earth's thermosphere. And as I recall, we did see quite a bit of a 27-day sort of rotation variation for that period of time. But then I was analyzing also what the response looked like to Mars in terms of the solar wind electron analyzer data. And that work is still in progress. I don't quite have an update there, but I think it'd be interesting if those events are impacting both the thermosphere of Earth and the one at Mars, seeing what the relative response looks like.
And did Erica get Mars on? I think there was like around May 6th. There was the CME that went off, so it'd be a little bit after that. You did show some Mars reactions to some of these CMEs, right, Erica?
Why do I forget to unmute? Yes, actually, so since I got the 1 minute thing already and I was like very behind, I couldn't explain very much about Mars, but if you want, I can like show a bit better that one slide and the Mars observations.
Yeah, why don't you do that?
Okay. Will I manage to share again? Yes. So it was this one. So basically, this data is from the solar wind only, so upstream data that Christina Lee sent me. Now the problem was that I'm up to like the first half of the month. As you can see, we don't have much upstream data. So what I did to try to complement data and try to understand a bit more is for the solar wind here, I complemented MAVEN with Mars Express data, which are the ones in green, which, okay, give us a bit less gaps filled. And also in the period in which we have both data sets, they're matching pretty well, apart from a bit difference in magnitude, but the profiles are very well matching, so we can be quite fine with it. And then basically so this very weird shading stuff in the background here. So in black thick line is the solar wind upstream data. In the background weird shading, that's the actual full data set. So all these vertical, every single tiny vertical line is one orbit, basically MAVEN entering the Mars magnetosphere, deeper induced magnetosphere, deeper and deeper. Obviously, the full data set goes to like tens of nanotesla because the closer we go to the planet, but okay, I cut it to like 18, I guess. So I think like 18 nanotesla, but and these lower measurements correspond to like force shock and like very, very outer layers of the magnetosphere. Now, what's going on? Basically now, even in this period, which is more or less from the 7th to the 12th of May, this background, which is actually the full cadence, like is the magnitude is of the measurements is elevated, which is actually also what happens here when the CIR passes. Like you see, like the full orbit data are still like higher than the undisturbed solar wind. So basically, that's by combining these two data sets and then seeing that also in the solar wind speed there is something going on. There is like speed increasing, so it could be an HSS plus this first CME. Yes, so from there, like we could determine that there were some disturbed conditions at Mars, even if we didn't have solar full solar wind upstream data. Yes.
Great. Thanks for going through that, Erica. And just so everyone is aware, as far as MAVEN is concerned, we will be continuing to observe at Mars for nearly the next decade. So we'll be able to observe the conditions both at Mars, but also within the solar wind at Mars's orbit through the upswing to solar maximum. We're working on our extended mission proposal right now to hopefully observe through solar maximum as well. So with that, I'm going to turn back to the Slido, and Janet Lumen, are you able to unmute and ask your question? If we can help her unmute.
She'll need to raise her hand. So yeah, if folks raise their hand, then Kelvin can.
Janet, can you raise your hand? There you go.
Okay, Janet, you should be able to unmute.
Okay, can you hear me?
Loud and
Yes.
clear.
Hi. Hi, Amelia. I enjoyed your talk. One thing that has always bothered me, though, and you brought it up in a couple of occasions, is the concept or problem of erosion at the interface between the CME ejecta and the CME sheath. And one can imagine that the amount of erosion differs significantly from event to event. And we don't really have a good record of propagation time modeling. And of course, many of the models don't have ejecta in them. So I wondered how serious a problem you think this is. Is erosion of the ejecta a big deal in both, the propagation characteristics of the CMEs as well as their ultimate planetary impacts?
Yeah, that's a really, really good point. I did not mention in my talk that this erosion can be very critical for the magnetospheric impact and interaction, because if you think that you are seeing something launched from the sun and you want to predict that what is its space weather effects at the Earth or some other planet, and then just in the interplanetary space, the significant amount of magnetic flux is eroding. So then it can change a lot the expected space weather impact. And I think now with these space weather modelings, like we are doing, for example, now the work with the Euphoria, with these magnetized CME models. So I think there should be some possibilities now to start looking this interaction in more detail with the previous solar wind, or you can probably even make some preliminary guesses if you know that you have the solar wind on the, or what is the, because it's dictated by quite strongly by what is the preceding solar wind to the CME and what is the leading edge magnetic structure of the CME. So if they are on the opposite direction, then you will get in the leading edge a lot of this erosion.
Right. So we have both the challenges of getting the ejecta properly modeled, but we
Yes.
also have the ambient solar wind, and we have this problem of the slow solar wind not being very well modeled.
Yeah.
So many challenges ahead, and I think the modeling will reveal at least the issues that that we are facing, and maybe allow us to parameterize or understand better with ensemble modeling what we need to do. But if you have ideas about observational work that could enlighten us as well, as far as the erosion problem is concerned, they would be very welcome. Thanks.
Yeah, there's some of these works done by, I think it's from Ruffenak, I'm not sure how to pronounce the last name, but they have been doing this statistical analysis of that at 1AU, that how much they see the erosion, but it's like mainly focused on the analyzing the observation as they are in situ, not so much about the predicting the amount of erosion in different settings. But it indeed is challenging, because not only have you need to predict what is the magnetic structure of the CME, you need to predict what is the field ahead.
Thanks a lot. Enjoyed your talk.
Thank you.
Great. And Amelia, there is an anonymous question that was posted in the Slido for you. So let me just read that out loud. It was, can you give more information about the difference in acceleration between the core and the cavity? And I think that was in reference to one of the slides that you were showing a plot. Did you catch that one, Amelia?
Sorry, I didn't hear anything.
Oh, no worries. There's an anonymous question for you in the Slido asking if you can give more information about the difference in acceleration between the core and the cavity.
Yeah, unfortunately, I'm not super much knowing about this part in Sanchita's study. I know she was building these J maps, and then she was tracking from there both the core and the CME cavity, and seeing these different profiles, and in the first core going more strongly, and she was hypothesizing that it's that when your CME is rising, if it has this strong reconnection from below, like all the time feeding it, then initially the core can like move faster in relation to the cavity. It seems that it's then like evening out at some point, but I think she was actually referring to the Ben Lynch paper. So I don't know, Erica, if Ben is here and you can ask more details.
He's in the living room.
So if somebody wants to know more, maybe I think it was his paper. But that's basically what I know about this core and cavity acceleration. But I think it's the kind of the interesting, since it could tell about the differences between these different structures. If you can like identify them from these J-maps or other observation and derived kinematics, you can probably tell them something about this physical mechanism related to the CME eruption.
Okay, great. And it sounds like we have a resource, a paper we can look at for more information too.
Yeah.
Okay, and with our final 2 minutes, I see Carlos, you have a comment in the Slido. Would you like to speak to that, and then we'll close the session?
Yeah, this was already answered. It was my confusion about kilometric versus decametric radiation. But the bottom line, I think, is the fact that in Jupiter, there is no influence on the radiation because the magnetosphere is very strong, while at Saturn, as Erica said, there is an influence. Is that correct?
Yeah.
All right, great. Well, with our final minute remaining, we're going to use that to thank our speakers and transition to the next session. So thank you, Erica. Thank you, Amelia. Thanks for a great discussion, everyone. Great job. Okay, and then I will pass this over to session 10. We have our chairs, Robert Allen and Mary Hudson.
Yeah, so hi everyone. So thank you for coming to our second session on high-speed streams. So on Tuesday, we heard multiple talks on kind of going from coronal holes out to interplanetary space. And today we're going to hear 2 talks focusing more on how those then impact planetary systems. And at the end of that, then we're going to have a nice long discussion period where we're not only going to talk about those, but then try to bring us all together and look at high-speed streams all the way from coronal holes out to ITM systems. So our first talk today is going to be from Mary Hudson. So Mary, I see you're on.
All right, so I will try sharing my screen. And so here we go. And now I just need to move everybody's picture so I can go full screen. All right, and now I'll move you all over. Okay, so thank you for the opportunity to actually make a comparison between CME and CIR-driven storms and their effects on the radiation belts. So my talk sort of fit in between the last working group and this one. So this is a slide that Janet Kozera showed, I think, yesterday, and I want to credit Shinlin Lee, my former PhD student, for creating this slide, actually going back to 2006 when there was only low altitude SAMPEX data showing greater than 2 MeV electron flux as a function of radial distance in the equatorial plane in Earth radii. And Shinlin over time just kept adding and adding to this plot. And fortunately, the amazing little SAMPEX satellite, which was a small Explorer class satellite, lasted until November of 2012, after the launch of Van Allen probes, which is in a near equatorial plane cutting through the radiation belts. And so it was possible to, oops, where did this go? Sorry. It was possible to merge these 2 data sets and get this 25-year time history of the outer zone. And so in the middle panel here, I won't talk about the DST or the GOES data that Janet mentioned, but you see the sunspot number, of course, and then the red curves are the solar wind speed weekly averaged over this whole 25-year time interval. And the thing I want to call to your attention that just strikes me as a radiation belt scientist is the very deep dropout in outer zone electrons during the last solar minimum during the period 2009, in particular 2009, 2010. And then let's see, is my arrow working? There it is, good. Contrast that with the most recent solar minimum where we had recurring high-speed streams, I'll show you in more detail, that continue to pump up the radiation belts. And you see those high-speed streams in the middle panel here that went down to much lower average velocities during the previous solar minimum. Okay, so this is a close-up now of 2018, 2019 as viewed by Van Allen probes, and this is 3 different energy channels now. The top one is basically the one I just showed you, and the middle and bottom are 2 higher energy channels. And all throughout this time period, 2018 into the end of Van Allen probe's mission in October 2019, you see these recurring enhancements in the outer zone, which are primarily due to high-speed stream driving. CIR driving. The exception to that is this time period indicated with the arrow in May of 2019. And there were actually 5 CME shocks during this time period, but the 13-14 May CME shock, and I'm identifying it by its arrival time at L1 as opposed to its time leaving the sun. The middle one of the 5 was the most geoeffective. And then this later event that shows up in particular down at the bottom in the most energetic electrons shown was due to the high-speed stream interval late August, early September 2019. So what we did was contrast these 2 types of drivers in doing simulations of the impact of the solar wind variation on the radiation belt. So first, let me zero in on the Omni data for this event. The one on the left is the May event, and it's a very typical looking set of Omni data for a CME shock. You see the rise in the solar wind velocity as measured at L1, And you see the dip in the interplanetary magnetic field Z component, which is a particularly strong geoeffective driver because it enhances reconnection at the dayside magnetopause and it enhances convection throughout the magnetosphere. And then you see the increased solar wind dynamic pressure and density that accompanies that shock. And this was identified as a shock in the Kane-Richardson CME shock table, as were the other the other four. And then this shows the location of the magnetopause, which moved into 8RE associated with this event. And this shows the SIMH index, it's called, which is a higher time resolution DST, if you're familiar with that, which is a measure of the buildup of the ring current associated with the enhanced convection. So this whole picture here would be a very typical looking CME shock-driven storm, although a modest one, DST, I think only went to about -65 CMH for this event. But this would be a typical event at solar maximum, and there would be larger, stronger ones at solar maximum. Over here on the right, you see the CIR-driven time interval. You see the rise in the solar wind velocity, which gets higher. This is going up to 800 rather than just about 600 for the previous event. And you see that the IMF-BZ now is characterized, instead of the kind of coherent structure you have on the left from the flux rope basically associated with this event, you have oscillatory IMF-BZ, which is characteristic of alphanic fluctuations that are very typical for this type of event. And these alphanic fluctuations in the solar wind, they look very rapid on this time scale, but they produce alternating southward IMF-BZ that drives substorms in the tail. And those substorms contribute to injection of electrons from the plasma sheet into the inner magnetosphere. So they're very important in the source of the inner zone, of the outer zone for this type of event. And then I'll call your attention to the bottom panel here. Again, my arrow is being a little flaky, but the bottom panel again is the ring current buildup, and now it is much more prolonged and gradual than the sharp buildup of the ring current seen in the bottom left panel associated with the CME shock. So this is the solar wind input that we use to drive a global MHD simulation, and we actually use two different simulation models to study these events. So the data at L1 is propagated to the upstream boundary of the global MHD code, and on the left you see the initial condition of the Gamera code we used, and we also used the Lyon-Fetter-Mowbray code and made comparisons between the two, and coupled them to the Rice convection model, which is shown down here in the lower panel. And this is a means of tracking more energetic particles that are followed in the MHD code that correspond to the ring current. And so you have different opposite directions for the drift of electrons and ions taken into account. And you have the faster drift of more energetic ions longitudinally taken into account with the RCM code, which is coupled to the global MHD. And then over on the right, you see the meridional cut, whereas on the left, the main panel is showing you the Z component of the magnetic field coming out of the plane, which is dominated by the Earth's field inside the magnetosphere. Over in the right panel is the initial condition of our test particles, which we sprinkle into the time-dependent MHD fields, which again are driven by the upstream solar wind plasma parameters and magnetic field parameters. And we have trapped particles initially, which appear as a completely filled in black annulus. And we inject plasma sheet electrons continuously from the tail. And that's the little red annulus, partial annulus that you see on the left. Okay, so now in order to compare this with observations, we have to weight the test particles, and you could weight them in energy and flux, but instead we weight them in phase space density, this quantity F, which is like the distribution function in a Fokker-Planck equation. It's proportional to the flux and divided by the momentum squared for equatorial particles. So we take the measured phase space density, which required converting measured Van Allen probe data from flux at a given energy into phase space density. This black curve corresponds to the initial radial profile of the phase space density that we use to weight the test particles in the simulations. And then we continuously update the outer boundary of our test particle simulation as the phase space density evolves in time. This shows the initial radial profile for the two storms, and you'll notice that the phase space density was 2 orders of magnitude higher to begin with for the CME shock-driven storm. And that had to be due to earlier enhancements in the radiation belt during the time period preceding it. Okay, so this is our result slide because we don't have too much time here. So I combined the results for both storms into one slide. And on the top, you see the CME shock-driven storm. And each one of these profiles that appears in color, and that was also the case for the previous slide, is from an orbit of one of the 2 Van Allen probe spacecraft that were in comparable orbits. And there were 2 available for the May storm, and only one of them survived for the September storm. It had been turned off in August. And the black dots correspond to our final simulation result. And we ran the CME shock-driven simulation for 11 hours for a shorter period of time because everything happens much faster for that event. But what I want to point out is that, and so therefore you should be comparing the green, which corresponds to the time where we ended the simulation, with the profile of the measured phase space density at that time. It does a pretty good job of capturing what corresponds to a decrease in flux at high L values, and this is due to loss to the magnetopause, and it's particularly evident when you look at higher energies over here at 5,000 MeV per Gauss. You see that your initial radial profile has gone down at high L values, but you get inward radial transport and see that at both first invariants. And so that's the dominant sort of recovery. And that's caused primarily by ultra low frequency waves, which are excited like the ringing of a gong when the CME shock impacts the magnetosphere. They're also excited by the Kelvin-Helmholtz instability along the magnetopause due to the high velocity shear there. Now, the CIR-driven storm we studied for 4 days because it was a longer event. So we simulated 4 days. And notice it's completely different in the sense that you have just a significant rise in phase space density from the blue initial orbit profile. And that occurs at both first invariants, stronger at the higher invariant. Whereas you had a decrease at high L values for the CME shock-driven storm. So for these CIR storms, you don't have the dropout of radiation belt flux initially that you then have to rebuild from, like you do for the CME shock-driven case. So that can result in higher flux levels for these CIR events. And I'll go back to that slide of Shin-Lin's to emphasize that at the end. I want to point out that one feature we are not able to reproduce with this type of simulation is the peak in phase space density. And that is due to local heating. There was Whistler mode chorus present at this time in both storms, in fact, later in the May event, that was responsible for local heating in addition to the radial transport that the ULF waves produce. So I'll just finish up with conclusions here. And here is this plot of Shin-Lin's. I'll just leave my conclusions up, but I want to point out that if you look at the solar cycle here in terms of the sunspot number, the declining phase is characterized by high-speed streams, which really stand out notably for the preceding solar maximum, 2 solar maximum ago, but was also present for the last for the 2003-4 solar maximum. And so you see, on average, these are 30-day averages of radiation belt electron flux. You have higher flux associated with the high-speed streams than you do with the CME shock events, although a given CME shock event can produce a stronger enhancement over a shorter period of time. And I could go in and name the ones, Halloween storm this, and we give, Bastille Day storm that, and so forth, that were associated with particularly strong CME shocks. And I'll finish just by commenting that this black curve that you see here is the location of the plasma pause, and that plays a critical role in the inner boundary of the outer zone. And that's very much controlled by the magnetospheric convection. And that in turn is controlled by the parameters of the solar wind. So if I could get my arrow to move to this, yes, there it comes. No, it just doesn't want to come down and live. But I'll point to the box just above the figure on the bottom right. EY equals minus VXBZ, that's the solar wind electric field. And a fraction of that couples into the magnetosphere in the reconnection process and drives the convection within the magnetosphere. So that convection determines the location of the plasma pause boundary. And you can see in the figure on the lower right that there's been some erosion, some time-dependent erosion of the plasmasphere that distorts its shape and affects the depth of penetration of the electrons. And so on the bottom left, you see during the very quiet solar minimum period shown here that the magnetospheric convection has been weaker, the solar wind velocity on average has been lower, so the plasma pause is much more extended. And that really is a boundary for loss inside the plasmasphere that limits the radiation belt electron flux, in addition to the mechanisms that cause its enhancement. Okay, so I'll stop there.
Thank you, Mary. Just like the other ones, we're going to hold questions until after both speakers present. But if you do have any questions, please put them in our Slido and we'll go through them afterwards. So our next speaker is Federico Gasparini. So Federico, are you on? I see you're on.
Okay, 1 second, Federico. It looks like you dropped off. We need to make you a co-host again. There we go. You should be able to share now.
Okay, hello everyone. Hopefully you're seeing my slide here. I would like to start by thanking the conveners for the invitation, and also my collaborators, and in particular Joe Hughes, as well as Jeff Forbes, for their contributions. In this talk, I'm going to be discussing ionosphere thermospheric response to high-speed streams observed during 2018 and 2019, and potential impacts on the Mars upper thermosphere. So the outline of this talk is the following. I will first provide an overview of the data model used. I will then discuss evidence of high-speed streams during the WHPI campaign, and also its impacts on the terrestrial ionosphere and thermosphere, and possible impacts on the Mars upper thermosphere. I will then provide a summary of the main results from a similar and related study that is currently under review by JGR Planets on solar rotation effects in the whole Martian thermosphere. So for this work, I'm taking advantage of thermospheric density from the precise orbit determination data from the European Space Agency's WRM-C mission, which is one of 3 satellites that was launched into a high inclination orbit in November 2013, as well as vertical total electron content data from 2 remote ionospheric observatory, or RIO 12 and RIO 15 GPS receivers that were developed here at Astra. And in particular, they were deployed around the geographic equator in August 2018 and provided over a year of data covering this period of interest. I'm also employing data or output from the specified dynamics whole atmospheric community climate model with thermosphere and ionosphere extension. And in this model simulation, the solar and magnetic forcing are specified using EF 10.7 and KP, and we're using the Healy's high latitude convection pattern. I'm also taking advantage of data from the MAVEN mission, in particular from the EUVM instrument, the solar wind electron analyzer instrument, as well as the NGAMS total mass densities. So on the top left here, panel A shows the time series of zonal mean as well as diurnal mean swarm C total mass densities that are average plus or minus 45 degrees in latitude during 2018 through 2019. We are looking at 2 years. The wavelet of that time series is shown in panel B, and the F10.7 is in panel C, the wavelet of the F10.7 solar flux, and panel D shows the wavelet of KP. What I marked here with the white box is the current rotation 2211 through current rotation 2215, which goes approximately from November 1st of 2018 through early March of 2019. You can see there is a clear 9-day variation in the densities that is also present in the KP. The May 2019 period that was previously discussed also shows a quasi 9-day variation in this global mean densities at low latitudes, but it shows a more prominent 27-day or so variation, which though is not clearly, well, you do see the 27 variation in the F10.7, but you don't quite see it as prominent the variation in KP. The plots to panel E, F, and G here show the solar wind speed as well as B total. The time series on the top in black for wind speed, and B total is in light blue. And so what you see in the wavelets is evidence of similar variations in the solar wind as well as B total. We are then interested in looking at the response on a global scale from the swarm C observations on a latitude versus time frame, and that's what showed in panel A on the right for the ascending node and panel B for the descending node. The curve, the red curve here, shows the superimposed AP, 3-hour day AP index, and you can see the strong modulation during the December through March time period, which becomes even most prominent around the end of this period here. But you can see that these variations are prominent at low latitudes, but extend also well beyond the low to mid latitude range as expected. The panel C shows the bandpass filtered version of the swarm C densities around the plus or minus 30 degrees in latitude. You can see that the amplitude is fairly large. In this case, we are able to capture most of the quasi 9-day variation around the beginning of the period and December period, which is the one that I'll focus in the later part here. You can see also the wavelet of swarm C and AP that demonstrates this 9-day variation. So we are then interested in seeing whether and to what extent the ionosphere is impacted by the high-speed streams observed during the December through March 2019 time period. And for this, we're employing the vertical TC from Rio 12 and Rio 15. Here I'm showing the local time versus UT time depictions for Rio 12 on top and Rio 15 at the bottom, panel A and B, whereas A prime and B prime show the results from WACA-MAX sampled at the measurement location. You can see that there is significant agreement. In fact, panel D shows the scatter plots that demonstrate correlation coefficients of 0.67 for Rio 12 and 0.72 for Rio 15. So we are then looking at both Rio 12 and Rio 15 for the from the period covering this strong CIR event. And here I'm showing the time series going from September 1st of 2018 through basically August 31st of 2019, the time series of Rio 12, panel A, panel B, Rio 15. And the periodograms and wavelets, panel A prime and A double prime and B prime and B double prime, what you see is evidence of a strong 9-day variation in the Rio observations that, of course, is also present in the AP, but is locked in the F10.7. We are then also interested in looking at what the response looks like as a function of local time, since we have all local times from these Rio observations. And that's what's shown here in panel A as a function of local time on the y-axis and a function of UT time on the x-axis. We are showing a 8-day to 10-day bandpass filter version of the vertical TC from Rio 12 on panel A and B for Rio 15. You can clearly see this modulation, which is present during the December through March period. We also performed a correlation analysis with the AP and demonstrated a 0.78 correlation coefficients, which indicates that over 50% of the variance in the vertical TC observed by Rio GPS receivers is due to these high-speed streams that are really dominating the dynamics around this period for the ionosphere. We are then also looking for a concurrent period of time, in particular during December of 2018, at the solar wind electron analyzer data from MAVEN. In particular, what's showed here in panel A is the electron counts for an energy level of approximately 55 electron volts. And you can clearly see that quasi 9-day variation in the electron counts that is evidenced by the periodogram on the right. At the bottom, we are looking at the NGIM CO2 density near 200 kilometers in the upper thermosphere. And despite the fact that we do have significant gaps in the data, unfortunately, in this December time period, a periodogram shows evidence of a 9-day variation also in the MAVEN thermospheric density. It will be interesting then to further connect these, but one of the issues there is that the EUVM data also shows a 9-day variation. So it might be hard to really disentangle the effect of solar irradiance versus the solar wind driven component. But since for NGIMs we have data even at lower heights, we may be able to look at altitude profiles to better investigate this aspect. One study that I mentioned earlier was recently conducted and is currently under review by JGR Planets, is focused on the solar rotation variation from the MAVEN, NGIMS, and MAVEN UVM data using over 5 years of data. And I won't spend time here in detailing the methodology followed, but the plots to the right show the relative change of flux and density relative to 35-day moving windows. And you can see that for different flux levels, in particular the 0 to 7 nanometer, 17 to 22, 0 to 45, and the Lyman alpha, you can see that strong quasi 27-day variation for a period of time in late 2015. And the corresponding variations in the NGIMS densities, CO2, N2, and argon. And you can see that the response is very prominent and it is persistent for all throughout the Martian thermosphere. We are then using a statistical method, combining all the 5 years of data or so that we have from MAVEN and producing plots that are like the ones showed here in the middle figure, wherein we are seeing the altitude of, in the y-axis and the slope in the x-axis, which basically represents to what extent the densities are reacting to the solar forcing in the different energy levels for different species. And so we find that the strongest response is at higher altitudes and during solar high conditions, and the stronger correlation is found near the subsolar point and the highest sensitivity near the terminator. So just to conclude, I demonstrated the strong high-speed streams driven variations in the terrestrial ionosphere and thermosphere during the November 2018 through March 2019 WHPI period of interest. I presented also early evidence of a potential impact on the Mars upper thermosphere, and also showed a summary from a recent study showing strong solar rotation variations in the whole Martian thermosphere. Although future work and current work is addressing to what extent we are able to reliably verify the connection to the high-speed stream for the 9-day thermospheric variability observed at Mars, and also what the overall impact is on the Martian thermosphere, and as well as compare this response with that of Earth, and extend perhaps this comparative analysis to also focused solar rotation variation periods. And it would be very interesting to see how the thermosphere of Earth and the thermosphere of Mars are impacted differently by both high-speed streams as well as solar rotation variations in the flux. With that, I'd like to thank you for your attention, and I look forward to addressing any questions you may have.
Thank you, Federico. So now we'll transition to our question and discussion section of the session. So we're going to change screens. So while we're changing over, I do want to say in the chat, there was a question about whether or not all these recordings will be put online for viewing later on. And Sarah Gibson to answer that was that yes, we'll be putting a set of YouTube videos online. So if you missed any of these talks, you can always go back and watch them later on. All right, so our first question that we have is for Federico, and it's from Ian Hewen. So Ian, do you want to unmute yourself and ask your question?
Yeah, sure. Thank you. Excellent talk, Federico. Always good to hear what you have to say. I was wondering if you could just comment a little bit on the unusual crustal region in Mars's southern hemisphere and how it would influence or affect different space weather effects. Thank you.
Yes, thank you, Ian. That's an interesting thing to look into. What varying lower atmospheric conditions in the atmosphere of Mars would impact the potentially the upper atmosphere. And one of the things that I will be looking into will be also how changing magnetic effects as well as tides impact the upper atmosphere of Mars. So I don't have quite a great answer perhaps to your question, but I think later on it will be for me interesting to look into how the waves propagating from below are being impacted and by variations in the lower atmosphere forcing, and how that translates then to variability in the upper thermosphere of Mars.
Yeah. Okay. Thanks. Thanks.
Yeah, and I see Gina Gervasio has her hand up. So Gina, do you want to weigh in on this one?
Yeah, that was a great question, Ian. And I can contribute more from the magnetic field standpoint rather than the atmosphere that Federico was talking about. But essentially, these crustal magnetic fields, as you were saying, Ian, are scattered across the surface of Mars, and they vary tremendously. So particularly in the southern hemisphere, there are some strong crustal sources. And what that means is that the interaction between the solar wind and the planet is always changing. And so not only is it complicated because the crustal fields are rotating with the planet, but it becomes even more complicated because Mars has seasons. There's a slightly greater than 20-degree tilt at Mars, similar to Earth. And so you have periods where the crustal fields are in the southern summer, they're jutted out into the solar wind. So they're free to interact with the solar wind and the IMF pretty regularly. But then in the southern winter, then they're kind of hidden, and you have more of an interaction with areas that have weaker or moderate crustal fields. And so this is interesting from the standpoint of considering how magnetic reconnection between the IMF and these crustal magnetic fields at Mars, interplay. And so we do find that there are differences based on whether the strong crustal fields are in the solar wind or not, or for a particular season. But we're still exploring these effects, and the MAVEN observations are really helping us to understand if the strong crustal fields actually drive the Martian magnetosphere as much as we think.
Interesting. Just as a point of interest, my father is a meteorite asteroid specialist, and one of the samples that he has is from that Mars crustal region. It was dislodged during an impact on Mars and ended up in Africa. So that's part of the reason.
Oh, wow. That's great.
So I believe the next question we have is for Mary from Sarah Gibson. So Sarah, do you want to unmute yourself and ask your question?
Sure. I think it's very interesting when we're talking about these high-speed streams to look back at their sources at the sun. And the ones Federico was talking about between November and March were the ones that were giving that periodic behavior, and they were sustained for a while. And then there was the disruption. The one that then was around from basically, let's see, August to November was the one that Ian referred to as Mr. T. And may I share my screen, Robert?
Yeah.
My screen real quick and I'll show you, because for me, a picture is worth 1,000 words. And are you seeing the picture of the UV and the solar wind?
Yeah.
Okay, great. Yeah, this is just sort of a really, Ian has this nicer on his poster, so go see his poster. But this is the coronal hole, and that was there. And so like this one here is in the July, I think this is July, this is August, September, November. This is the time period that Mary was saying had the big radiation belt impact. And you notice how Mr. T, this coronal hole here that was there very nicely for 4 months, was looking the most T-like. And more than that, if you look at Ian's and Barbara Emery's map backs, just using potential field ballistic type models, just as a first attempt, you can see that the location of the Earth at that time was north, and the foot points were all in the crossbar of the T. And so the result was that we were sampling right across this horizontal low latitude structure and had a very broad solar wind impact. And so I guess my question for Mary, so just laying this out, and you may have said this, but maybe you can remind me, how did the impact vary over the 4 months when there probably was connection to this coronal hole and this high-speed stream? And would you agree that it's because of this very long, sustained, constant horizontal connection in the high-speed region that we had the impact we saw during the month that you saw it?
Yeah, so certainly the long sustained period for that second rotation there is the reason that it was more geo-effective than the one before and after. But all 4 of those appear in the Van Allen probe data, I believe, in the slide that I showed of the slightly less than 2-year summary. So host wants me to start my video. Sure. Wait, what happened? I don't know what happened.
We see you now.
Okay, all right. But at any rate, yeah, the answer is, the short answer is yes. The length of that event, as well as the strength of the driving in terms of solar wind velocity, which got quite high, higher than for the CME shock event in May, was the reason that it was the most geo-effective.
Excellent. And again, you can see Ian's poster. He has these type of maps for the entire 13, 14 months.
Right, and I'll definitely add a sentence on this to the space weather paper. Yeah, thank you.
Cool stuff.
Great. So I think that actually those are the only 2 Slido questions we had gotten for this session. So with that, I mean, if anyone does have any other comments or questions, please feel free to raise your hand. But seeing as this is where we are, I kind of want to broaden this out now more and actually kind of follow on with what Sarah just brought up of trying to tie together the discussions we had on Tuesday with those on planetary impacts today to kind of look at the connections we can bring. And so I think actually that event that you're looking at was a really nice example of this, of how we can tie together the coronal hole pictures all the way to the radiation belts. And so I know we kind of put together a few discussion questions we could ask during the session. And one was kind of, if anyone has any ideas of why there were more low latitude coronal holes during the 2019 solar minimum than the 2009 to drive high speed streams. So have we kind of done a comparison of why we might have these differences between different solar minima? Has anyone looked at that?
Yeah, certainly not why, but it's clear to me. I have done some comparative minimum work, specifically looking at the coronal holes, the number of them and their areas. And there are significantly more and in many cases larger low latitude coronal holes during this minimum. I would love to know why.
And that's really the reason. That's really the reason that this minimum was more geo-effective than the previous one, where the radiation bulb essentially went away at 2 MeV.
Yeah, I think it's interesting because I know on the poster I'll be showing later, we've been kind of comparing some of the CIRs we've been seeing as far as the superthermal particles associated with them in the solar wind. And actually, we've seen that they've kind of been less intense this solar cycle than the previous. And so it's interesting that from in the solar wind superthermal particle standpoint, it seems that we've been, less intensity associated with these. Janet Lumen, I see your hand is up.
Yeah, I'm trying to get there we go. I think it probably has to do with the strength of the higher order moments of the coronal field relative to the polar fields and the differences between the two cycles. When there's a lot of pseudostreamers, there's a lot of low latitude coronal holes. So, what we should probably do is look at the comparative pseudostreamer contributions for these two cycles and determine, the topology of the corona that's mapping out into the heliosphere. I think that would shed light on these differences. There have been a number of talks that use the potential field source surface modeling. So maybe there could be a working group that focuses on that question of the comparison and the contribution of pseudostreamers. Just a thought.
Really, yeah, I think it would be really interesting. Pete Riley, I see your hand is up. Did you want to chime in?
Sure. Just to follow on from what Janet said, we have the global MHD models which connect the entire magnetic structure of the corona, at least up until the orders that we can keep within the calculations, and we produce the speed at 1 AU. So if the speed matches at 1 AU, there's a direct connection between the driver in the photosphere and these high-speed streams at 1 AU. So I think that would be one way, and I've not done that, but we have all the simulations available. I could certainly help someone do some analysis, either looking at the different orders of the coronal field or otherwise putting together some kind of analysis. The other thing is, and I guess this is what Sarah said earlier, is that the previous minimum 2008, 2009 wasn't just one point in time. There was quite an evolution between 2008 and 2009. So depending on where you pick, there may be differences there too. That's it for me.
Sarah, do you want to?
Yeah, following up on that, it was interesting, 2008 and 2009, it was that long extended solar minimum, very deep, very long. And the interesting thing about 2008 versus 2009 was that they both had essentially no sunspots, hundreds and hundreds of days of no sunspots. And so if you were measuring them based on a sunspot index, you wouldn't really distinguish them, but they were very different. In 2008, there was quite a lot of structure still, quite a lot of tilt to the heliospheric current sheet, a lot of, there was a low latitude coronal hole, high speed stream, periodic forcing, and so on. And then it evolved in 2009 to something, it was as if, the question that had been going and still is out there is, and which I think we're going to talk about tomorrow, is what is the true ground state of the heliosphere? What would it be like if we had a Maunder minimum for a very long time? And one thing that has to happen, and this was what Yiming was talking about, is for that active region flux to decay. And so by 2009, it was a much simpler, more uniform, more axisymmetric structure, but still kind of a messy one compared to the tight dipole of 1996. So what's interesting is that during these quiet time periods, it's not just a single point of time. There is an interesting evolution. There was one evolution that happened last time from 2008, 2009 to this kind of warped, very prominent pseudo-streamer type structure into something which was much more diffuse. And then this time we had this evolution from this periodic structure to a large coronal hole, but we never completely simplified in terms of things like coronal holes. So each minimum has been different, and the impact is felt throughout the heliosphere.
All right, thanks for that. Great. So again, if you have any questions, so Janet Lumen, I see your hand is up again. Do you want
to? Okay. Can you hear me?
Yes.
Okay, so yeah, I think it's important, and Sarah brings this up. Sunspots are not what we want to look at necessarily. The magnetograms and the synoptic maps are what we want to look at. And you can see unipolar biases and distributions of unipolar biases from leftover decayed active regions still hanging around and being redistributed by diffusion and differential rotation. And so those patterns are critical in determining the coronal structure. And maybe we should focus on what the differences are in those unipolar regions, which are basically containing the footpoints of the coronal holes, the open field regions. And I think the important thing is to become intimately familiar with the magnetograms and the synoptic maps for these different cycles and how they change with time throughout the minima. Just a suggestion.
I think that's a really good point. So I see on Slido, Claudia had a question. So Claudia, do you want to raise your hand so we can unmute you? You can ask her a question.
Hi, thank you for your very nice talks, very interesting topics that I'm pursuing in my work. Thank you very much. I'm very excited with this subjects about solar wind, and I'd like to know from Mary about the electron, the particle results that you presented. Which is the most relevant feature between 2018 and 2019? Which year was more active and more relevant? I'm interested in this result to my studies on ionosphere response to high-speed stream. And thank you again for your very nice talk.
Well, thank you. Maybe let me share my screen if I may, and I'll pull up my presentation again, just to go to the relevant slide really is, and all of this is available. I think Catherine has collected these. So this is a summary slide that Allison Janes provided of the relativistic electron-proton instrument data. So this is the electron data. And if you look at the lower energy channels, the approximately 2 MeV, which are comparable to the GOES measurements as well, that people may be more familiar with, you know, there's a lot of similarity between the 2 years. There was, you know, more intensity of events, I would say, during the during 2018, and we really sunk into solar minimum in 2019. And yet there was this recurring Mr. T interval here at the end of 2019. And it, in fact, produced the strongest, most energetic, I should say, enhancement, not this, clearly the one in September of 2018 was very strong. And I remind everybody of the Russell-McPherson effect. So there's a strong equinoctial effect of the orientation of the Earth's magnetic field relative to the Parker spiral, say. So that September and March, sometimes March, but not this March, although there were enhancements and effects of the coronal holes in March of 2019. Things were still a little bit more like 2008, perhaps in 2018. And the thing about 2019 is that it just didn't get as dead quiet as 2009 did. And furthermore, that this event in the middle of Mr. T produced a very hard spectrum, we call it a very energetic enhancement that had not been seen since the September 2017 storm. People may remember from the beginning of September 2017, a strong CME shock-driven storm.
I'm seeing that there's a shadowing May, perhaps on May, September, October, and 2018, and we are studying some geomagnetic storms during this period.
Yes.
In the third panel.
Yeah,
you can see
these guys right here, right. And again, these are CIR driven.
And on the May, and it's very interesting result. I'd like to have a time to discuss with you, if possible, in another time.
Yeah, sure. Breakout room or something.
Okay, thank you very much.
Sarah, your hand's up. Do you want to add to this?
Yeah, actually, I wanted to ask Claudia a question. Claudia, am I remembering right that yesterday maybe you mentioned that you didn't see so much the 9-day periodicities in the ionosphere? Is that right?
Yeah, yes, it does.
So you saw Federico was showing some periodicities in the thermosphere, and that was from the time period from about, Federico, was it like October to March, or what was your time period again?
Yeah, but I think that Federico presented for 2019. I suppose.
No, I can share my screen again, perhaps, and show that period.
Sure.
Let's see. Oops. So here, yeah, we're looking at the swarm C densities going from January 1st of 2018. So we're looking at 2019. And if you're looking at the periodicities here, we're seeing from, say, 3 days to 30 days. You're seeing that, in this analysis, we're seeing the strongest response around that December 2018 period, around 9 days. You see that May period here of 2019. But in general, that's the reason why, I started focusing on that time period, because they really showed the most prominent response in the densities. I also looked into some of the ionospheric data, but unfortunately, what I have here is just for the September, 1st of September 2018 through March 2019. And in this case, we're looking at 2 GPS receivers. I've also looked into some of the more global scale TEC, and they still, for what I recall, showed the strongest periodicity around that November 2018 period, as opposed to the May event, for example.
Yes, I remember that in September, October, November, we have moderate geomagnetic storms. But in December, there is a weak geomagnetic storm caused by high-speed stream CIR. It's interesting, your result for 2018. And there are some weak storms that we noticed that they influence in the ionospheric response. But our focusing on is on moderate storms, in which we can see these periods in on the ionospheric TC variation. It's a very interesting connection with high-speed stream, and we are comparing 2008 and 2018 because there are some differences in the period. The most strong or most relevant periods. In 2018, we see clearly the nine days, but it's not so prominent in 2018. So we are investigating the cause of these differences. But your results are very important and interesting for our studies too. Thank you for sharing.
Sure. Thank you for that comment, Claudia. And I do recall seeing differences in the TEC response depending on what latitude you're looking at. So another aspect to, I think, potentially address is to what extent we are seeing that response, at different latitudes. In this case, you're looking at the geomagnetic equator approximately, I think, plus or minus 3 degrees in magnetic latitude. But those effects are really global, and I think better characterizing them would be something that could be done.
Okay, thank you.
Thanks. And Carlos, I see your hand is up. Did you want to add to this discussion?
Yes, basically related to what you just said, Federico, my question is how representative this data you have? I guess these are Astra receivers, so you were testing them. But if you were taking a global, regional receivers, let's say in the Aurora region or at mid-latitudes, would the results be the same? Or if you were to do like a global average, all the regions, what will be happening?
Yeah, thanks for pointing that out, Carlos. In fact, before I started looking into the Rio receivers, I looked into the Madrigal TEC covering the entire the Americas and actually averaged that data set, and that really showed a marked 9-day variation there. That in turn prompted me to look into this other TEC data, but it is there and it is global, the response. Yeah.
Okay, thank you.
And I see on Slido Liang, you asked a question. Do you want to unmute yourself and ask Federico your question?
Yes. So Federico, so if there's more crust area in Mars, on the Mars in the southern hemisphere, so would the high-speed stream effect would be more? You can see more effects in the southern hemisphere.
So that's something that I have not looked into, but I will defer the answer to that maybe to someone who's more familiar with the magnetospheric response. But I would say that one could expect a difference between the northern hemisphere to the southern hemisphere Mars also, potentially due to the different response in to the high-speed streams due to crustal effects. But that's something that that I think it should be my list of items to look into. But in terms of should we expect that? I think one could, certainly, as far as I'm.
Yeah, I would imagine that if there's more crust, then there's more like a magnetosphere effect, more currents, electric field, this type of thing. So it would have more effect in the southern hemisphere. That's what I imagine. So probably you would be able to see more like a 9-day periodicity in the southern hemisphere.
Right. And one of the things with the ANGIMS data that I've been looking into is that you have a precession in latitude. And I forget exactly what the precession cycle is, but it is also 200 or over 200 sols or days. And so I'm not sure what that latitude coverage looks like for this period of time, but it may be not non-trivial to see the response in both hemispheres necessarily and detangle that effect. But that's something that I think could be interesting to look into, potentially leveraging other data sets.
Yeah, and not only the hemispheric difference, and also I remember Gina talk about the seasonal, if you just looking at the southern hemisphere, you should see the seasonal difference as well, as you see the southern hemisphere. looking at the southern hemisphere, there should be seasonal difference.
Right. Yeah, and all those considerations are important when you're, I think, trying to assess the impact. How how seasonal effects as well as latitudinal effects are playing a role in that response. Absolutely.
Mm-hmm.
Okay, so with that, we are at the end of our time period for this session. And so we're going to go on a 15-minute break. When we come back, it will start the poster session. So I'd like to thank both of our speakers again and everyone for partaking in the discussion. So thank you all.
Thank you, Robert. And just to remind people, poster session is back here in this room. So we're not going anywhere else for the poster session. We sent you the link so you can look at them in advance, but come back to this room because it's from here that you can go to the breakout rooms to talk to the poster presenters. So see you in 15.